Hey everyone, this is Daniel for Rock the JVM, and in this video we're going to learn about stage actors in Akka Streams inspired by some real-world experience. So the objective of this video is to show you an example of where graph stages in Akka Streams are particularly useful for a custom scenario. And the assumptions are that you know some Scala and Akka Streams fundamentals, both of which I teach here at Rock the JVM if you're interested. And as recommendations, you should follow the code and replicate everything that we have here in the GitHub repository, which I'm going to link in the description to this video. And whenever you need to refresh your memory, just refer back to the video or to the written form at the blog with the link in the description. So here's the situation for you. A good use case for using Akka Streams is to read messages from a Kafka topic, which is a popular connector with Akka Streams, and then commit when you're done processing the messages from Kafka. So you need to subscribe to a topic, you need to process these messages according to your own business logic in a separate actor, and you need to send the messages to a sink, which will instruct Kafka to commit. Now, depending on your requirements, this may or may not be an easy thing to do. And as general requirements, we have a few. First of all, the Kafka commit must not happen until the processing in Akka is completed. So the business logic must have finished processing before you need to commit. The next requirement is that you must have complete clarity over states and outcomes. For example, you must not confuse a long time processing with an error state. And I'm going to give you an example in which that's the case and which we must avoid. Additionally, any error in the stream must also be propagated to the actor part because that's the business logic which absolutely needs to have full context of whatever happens wrong in your stream. And one other item which may not necessarily be connected to the business logic, but rather with the infrastructure, is that the inbound and outbound rate of processing messages should be decoupled from the messages from Kafka. In other words, the actor should be able to handle more messages than the ones from Kafka or fewer messages than the ones from Kafka. And I'm going to give you some examples for that. Now, an immediate solution for this sort of scenario is a simple source to sink plugged. So we have an actor-based sink that is very easy to write and that has custom logic for handling incoming Kafka messages. And the code would look something along these lines, where you have a source that simply reads messages as a Kafka consumer, and then a sink, which is a sink.actorref with backpressure, because you also need to handle backpressure in Akka Streams, which pushes all the messages to a target actor, and it has an internal protocol on how to handle backpressures and acknowledgements. However, there are some drawbacks to that. First of all, for all practical purposes, the sink should have auto commit enabled. Otherwise, it's really hard to write and the actor logic becomes super complex. And it's also impossible to decouple inbound and outbound message rates, which was our last requirement. This is strictly in a one-to-one correspondence from messages to Kafka to the messages that the actor can handle. So this is not necessarily suitable for us if we want some custom logic. The second solution would be an actor-based pass-through flow with the ask pattern. This is a little bit more complex, but this gives us some additional flexibility because we can separate the business logic in a separate actor, and the flow shape in the middle communicates with the actor, therefore handling the business logic separately, and can commit conditionally by sending actor replies to the sink or not. So we can skip the messages by not sending them to the sink, and the sink can take care of Kafka commits itself. The code would look something like this, where the source and the sink would look very similar, but in between them we have an actor flow, which is an ask pattern. So we have an actor flow.ask, and we have our custom business logic inside as a future. Now, the drawbacks to this little architecture is that the ask pattern, as you probably know from Akka, needs a timeout. And that can create a confusion between a message that takes a long time to compute or process versus an error state, and that can cause serious problems in critical systems. The second drawback is that due to the construction of Akka Streams in general, so not necessarily for a particular business purpose, the errors inside the streams will tear down the stream without giving us the opportunity to produce any sort of side effect or to propagate them to the actor, which might be critical for logging or for understanding what went wrong in our system. Also, there's only one-to-one association between the Kafka message and an actor reply because we work with the ask pattern. So there's no way to decouple the inbound and outbound rates. So after this 5-minute analysis, you quickly arrive to a more complicated but better solution to use a custom flow-shaped graph stage. So we are going to build a custom component in the shape of a flow that will receive incoming Kafka messages and it will push outgoing replies to the sink, therefore separating the commit logic in the sink from the business logic in the graph stage. And it will give us the ability to separate the inbound and outbound rates because this graph stage will interact with a target actor with a custom protocol. So because this actor is completely separate, we can invent our own protocol and make the actor send as many or as few replies or messages as we like. Obviously, there is a trade-off, and the GraphStage API is an extremely powerful, high control, but low level and high labor API, which I also teach in my Akka Streams course in the advanced section if you're interested. And we also must create a dedicated protocol for back pressure and the communication with the other stream components. Now, with this kind of diagram in place, I'm going to show you an example code of how that would work. So here in my IntelliJ IDEA, I have a little bit of code with Akka Streams, and at the first glance, this might seem a little bit overwhelming, but I'm going to walk you through this code, and we're also going to do a demo run. This code is replicated from the GitHub repository courtesy of my student and software architect, Niklas Urberg, who also wrote the blog post for this video. Now, at the top, we have stream to actor messaging, which describes some case classes and case objects. They are the messages between the GraphStage custom flow and the actor which backs that and with the business logic. So this is the custom protocol between our custom flow and the actor that does the actual work. After that, we have flow messages, which are the messages that flow through the stream itself. The invocation is the simulation of a message that's incoming from Kafka with the name as a string. For example, you can consider this name to be the key. And the response would have some data inside. For example, for the same key, we have some particular data or payload that we might want to store in a sink and instruct the sink to commit to Kafka. Now, this code is not connected to an actual Kafka source or sink, but it can very easily be connected to a Kafka because the logic is very similar. Adding some extra Kafka would have probably complicated this repository, and our focus is on the Akka Streams bit itself. So that's what we're going to focus on as we proceed. So this is the protocol, stream to actor messaging and flow messages. I'm going to describe every single one of these as we describe the components. The application itself is called stream with stage actor, and this contains a bunch of bits. This stream with stage actor will have an apply method which will start the root actor of an actor system. So at the very end of this little object, we have the main application which starts the actor system with this behavior. So the behavior itself will simply set up an Akka stream and will spin up the necessary components. So for all intents and purposes, the body of the apply method is our application. So the components are as follows. We have some boilerplate, which give us access to the actor system. We have a target actor, which is the actor that's responsible for the business logic. So the target actor is the business logic actor here at line 48. And then off of this business logic actor, we build a flow.fromGraph. And this actor ref back pressure process flow stage is a custom data type that we've built, and I'm going to describe how that works. And this is essentially the custom flow component, which is connected to the target actor, and it will be plugged in to a source and a sink. And the source itself is just a source of numbers that can fail upon reaching a certain value, and it will log so that we can identify messages in the console. So this source 123 map whatever, this is the equivalent of the Kafka source that will give us some initial data. Via actor flow, this is the custom flow that we have outlined in the previous diagram. We have a recover bit just in case we get some error in the Akka stream itself. We're going to see what happens with and without this recover bit. We're going to log everything, and we're going to run with something that would ideally commit to Kafka, so an auto commit sync, but we're doing with sync ignore because we don't really care about those bits. We only care about the custom actor flow. So everything else is pretty much boilerplate, the source 123 with the map, as well as the recover, just in case we have something wrong in the stream. The logs and the sync and ignore are all boilerplate. Now this whole construct, source 123, map, via flow, recover, log, and run with, This is an entire Akka stream. So when we say run with, this automatically creates the Akka stream and starts it or allocates the appropriate resources. If you are familiar with Akka Streams or if you've taken the Akka Streams course from Rock the JVM, this expression will be quite familiar to you. This returns what is called a materialized value. And this materialized value is a future of an ignored value called done, which allows us to monitor when the stream has been completed. And we do that with this stream action.onComplete so that we can log some more. So the application itself is not really that difficult. There's a lot of boilerplate involved, which is why I preferred to show it to you directly rather than type it manually. And in main, as I described, we're simply spinning up this root actor system with this little behavior because that's what the Akka typed API forces us to do. So the application is pretty much covered. Our goal is to focus on this actor flow, which is this flow dot from graph, and the logic itself is this actor ref back pressure process flow stage, this one big of a mouthful, and the target actor itself. I'm going to focus on the target actor first. So I'm going to minimize the application because that's done. The next bit is the target actor. The target actor is the so-called business logic in our application, and I'm going to simulate something that's going wrong in this actor so that if something fails in the business logic, it will tear down the entire stream, and also the situation in which this actor might send fewer or more messages than the messages that it receives. So this target actor is a simple actor which counts how many messages have arrived so far. And the behavior is given by the apply method, which is a behavior of this stream to actor message, which we described at the top, this stream to actor message. This is the trait, and the target actor will support this entire protocol. Okay. Now the apply method returns a behavior, which is behaviors.receiveMessage. Behaviors.receiveMessage is just a partial function that will be applied to every message that will be sent to this actor. We have two that are most interesting. One is called stream init, and this is part of the protocol, stream init. And if we have stream init with an actor that this actor will communicate to, this actor will receive the stream act. So we're going to send a signal to this reply to actor. So we need another actor which this target actor will communicate to. This is going to be the internal actor of the GraphStage flow. So we have an initializer message, so this will establish some sort of a handshake with the GraphStage component, and it will keep the behavior the same. And then when we have an incoming element, we call that stream element in, which is essentially a wrapper over the quote-unquote Kafka message, the invocation, and the actor which will receive the final replies. We're going to have some logic inside. So we're going to simply count the messages. So counter plus equals 1. We're going to simulate something bad happening if we have some sort of condition. And we're going to simulate multiple messages being sent to this reply to actor if we have some other conditions. So these are simulations of something wrong going with the actor and something else going on with the actor that will lead it to send multiple messages for a single incoming Kafka message. So we're going to simply fill these messages with some data. And we're going to also send an acknowledgement message so that the GraphStage actor will be in charge of the communication with the other streaming components. Then we also have stream failed and stream completed. These are infrastructure-related messages which we've already built here in the stream to actor messages. So we have stream completed and stream failed. These are signals for when the Akka stream has already been successful or failed for some other reason. So notice that one of our requirements to propagate something erroneous happening in our Akka streams is automatically broadcasted or propagated to the target actor. So if we have some failure in the stream, this actor will be notified and we have something that we can do in case the stream failed for whatever reason. So we also have this possibility. The absolutely famous ASCII diagram of how these things work is depicted in this little comment here. So everything upstream is the quote-unquote Kafka source, which will send messages to this graph stage, and this graph stage will communicate with this target actor with the internal protocol that I just described, and the target actor will send it back whatever results of processing to the graph stage, which will send them further downstream for the sync and for the rest of the stream. So the big mouthful graph stage is this actor ref back pressure process flow stage, which extends the GraphStage API. The GraphStage API is extremely powerful, but extremely laborious and low level. So we need to be careful with some lifecycle methods. Here's how this graph stage is being built. First of all, we need to type this graph stage with the kind of shape that it will have, and we'll have a flow shape of the same type. So we'll receive messages from the upstream and we'll send back messages downstream of the same type. Okay, now we need to have an inlet and an outlet to define where we are going to read the messages from and where we're going to put replies to. So this is what we need to do here to describe in and out. Now, the core of this flow stage is this function called createLogic. I'm going to minimize that for a moment, just that you can notice how important this createLogic thing is. The only thing that we need to define otherwise is the shape, which is the flow shape, which is constructed out of this inlet and outlet. So the crux of the logic of this graph stage is described by the createLogic method. And the createLogic method will have some internal variables because this may be a stateful component, so variables are fine. And I separated some sections here in this createLogic method. First of all, we have the stage actor, which is a fake actor that can be used to communicate with the target business logic actor that we've described before. So this can be set as a destination for replies from the business logic actor, so the one at the top. And the replies from this actor can be sent to this little self, which will propagate them downstream to the rest of the stream components. And I'm going to show you how that would work. So assume we had a self, which is a reference, an actor reference that will be used to communicate with the target actor. This is also in charge to send the messages downstream. We also have some lifecycle methods in the logic of this graph stage. We have pre-start and some handlers from input and output. Let me take them in turn. So let's take the stage actor receive logic first. All right, now the stage actor receive is being given by the receive message handler that will handle the messages from the business logic actor above. So the partial function that's relevant here is this message with sender. So the pattern match is case actor ref and the message, and then you'll do something when you receive a message from some actor. And if we have a stream acknowledge, then we're going to call this onAck function, which can either pull items from upstream or complete the Akka streams if necessary. And we're going to explore what these methods will do. So we have handlers for stream ack, for stream element out. That means that the business logic actor has already pushed some sort of reply to us, to the graph stage component. So we're going to push it further downstream, which is done by this function called emit at line 152. So this pushes an element outstream through the outlet. We also have a version called stream element out with ack, which also means we need to check if we can pull elements from upstream as well. And if we get a failure or a terminated, which are automated messages sent by Akka because we're monitoring the target actor for death. So if the actor dies for whatever reason, we're automatically being notified with this failure or terminated messages. And if that's the case, we're going to finish or terminate the stage and therefore the stream. So if our business actor dies, then we need to finish our entire Akka stream, and that's normal. Okay. So this was the stage actor receive. So this is the internal logic of the internal actor of this graph stage piece of the Akka stream. The self thing can be used as a reference in conjunction with the target actor. Okay. Now, let's move on to the lifecycle methods of this graph stage. We have a lifecycle method called pre-start, which will start up our target actor and will send an initial message. So tell a target actor to say stream init, and give the destination or the reply actor back as self.ref. So the target actor will communicate back to me when it receives stream init. And we're going to send a variable here for expecting actor true so that we know whether to start pulling items from the upstream. Okay, so that is a lifecycle method called pre-start. There are other lifecycle methods that we can implement, but that's not necessary for what we need to do. All right, now, two very important things that we need to do in a graph stage logic would be to set handlers for inlets and for outlets. That means what happens when we receive a message and what happens when we want to push a message to the outlet handler. All right, let's look at the in handler first. So the handler has some lifecycle methods called onPush, on upstream failure, and on upstream finish. OnPush means that somebody upstream, that is the source, pushed a message to us. So the Akka Streams component, this GraphStage, will simply grab whatever element it has, it will push it to the target actor, and it will expect an acknowledgement back from the target actor so that I can push the reply further. If we get an upstream failure, then that means the source failed, and therefore I'm going to tear down my resources. And likewise, if we have on upstream finish, then I'm going to clean up my resources nicely. So this is the handler. The important method is on push, where we need to grab an element that is from quote-unquote Kafka, tell the target actor that we've received an element, and expect a reply back. Okay, so this is the handler for the inlet. We also have handlers for the outlet, and that is on pull. That means that the downstream sink will give a demand signal. And if that's true, then I'm going to try to pull an item from upstream myself, and likewise send it to the actor, and so on and so forth. And when we have a on downstream finish, which means that the sink has terminated, then I'm going to clean my resources nicely. So these are my lifecycle methods, pre-start, and the handlers for inlet and outlet. And the auxiliary methods that are necessary here: pull if needed, complete stage if needed, unwatch, tell actor, and terminate actor and fail stage. These are auxiliary methods that are used repeatedly in my code. So for example, pull if needed, I'm going to check some flags here, and not has been pulled. I'm going to try to fetch an item from upstream, that is from the source. If the source has already sent something to me, then I'm going to return an element in the in handler so that the element can be grabbed later. So that's the general gist of pull if needed, complete stage if needed, and terminate actor and fail stage, which are essentially resource closure methods. And we have unwatch and send completed. We're going to simply unwatch the target actor, and I'm going to tell the actor to stream completed so that the actor can terminate as well. If the target actor receives stream completed, the actor will be stopped as well. So the behavior stopped, therefore instructing Akka to clean up its resources. So this is essentially what happens in this custom GraphStage component. So with this situation, we're essentially simulating all our requirements that we described in the diagrams, where an actor can be decoupled from the Akka stream, it can fail, and it can instruct the stream. The stream failure can instruct it if we have a stream failed, and we can also decouple the rate of message receiving and message production. So this is essentially a complete application. And in stream with stage actor, I'm going to uncollapse my code again. I'm going to run my first application. Here's how the application is supposed to work. If we have source 1, 2, 3, and we're throwing an error in case we get a 4, then the stream will be successful, and the target actor should process all the messages from 1 to 3. The way that the target actor will process all the messages from 1 to 3 is that if counter is bigger than 2, that is for the third message, we're going to see 2 messages instead of 1. So message.name will have count 3 and with 2 items instead of 1. If we modify the cases here, and if we comment and uncomment the recover bits, we're going to see different behaviors. Let's do the happy path first. So I'm going to run my little application, and we're going to inspect the logs shortly. So here's what the logs will say. Received stream init will signal demand by responding act. So the actor was correctly started. Then we have step 1 before the actor flow with value 1, step 1 before actor flow with value 2, step 1 before actor flow with value 3. These steps are being logged in the stream action here. So in case we get messages 1, 2, 3, this log line will be printed out. So this is from the source. With every new incoming message, the actor itself, the target actor, received invocation name 1, invocation name 2, and invocation name 3. So the target actor successfully received the wrapper messages for all of these items. So value 1, 2, 3, we have invocation for name 1, 2, 3. Okay. Now, for invocation number 3, we should be seeing 2 replies back. And here under the log flow, we have got response, respond, name 345 and name 368. These are the 2 responses just for item number 3. So the target actor successfully skips some messages, and for one message that was important for us, we sent multiple replies back, and they were successfully processed by the later stream components. After that, we have some nice cleanups. So we have stream completed, we'll clean up and stop, upstream finished, and stream completed successfully just for graceful shutdown. Now, I want to demonstrate something else because this flow that we have just seen here demonstrates the decoupling between the actor that is in charge of the business logic and the stream itself, also from the point of view of RAID production and consumption. So as you can see, we have multiple messages for the same request and potentially no messages for some other requests. Okay, now I'd like to demonstrate how an error from the stream can be propagated to the actor itself. So let's assume that the source throws an error for item number 2 for whatever reason. So we have step 1, 2 arrived, will throw exception, and 2 is a bad number. In that case, the upstream will throw an error and the actor will be notified in that case. Let's see. All right, so we have some stack traces here. The logs are important. So we have log started, and so on and so forth. We have stream init, we have step 1, and then we have invocation 1 arriving at the target actor. Then we have the throwing of the exception here in the source. And notice that the target actor, this log line is super important. The target actor received the notification that the stream failed, and we can add a reason or an error here. We'll clean up and stop. So notice that the actor was successfully notified of the failure of the stream. Obviously, we're going to also log the entire stack trace to figure out what went wrong, but the business logic can also recover or handle that error case and wait for the stream to start again or some other logic that's relevant for you. And likewise, if the actor itself fails, then the stream will also fail and the resources will be shut down gracefully. So let me go back to the target actor and I'm going to modify this counter. I'm going to throw the error here at counter equals 3. So for the third message, I'm going to throw illegal state exception saying 3 is a bad number from target actor. And I'm going to run this application and we're going to see some different logs in our little system. All right, so we have some stack traces. Let's trace the logs again. So we have stream init, step 1, value 1, invocation. So this went nice. Step 1 for value 2, the invocation arrived successfully. The source sent the value 3, and notice that at this point we have 3 is a bad number from target actor. Okay, now at that point, we have a failure in the target actor. So after all these stack traces, which are related to the actor itself, we have a terminated. Notice that we have a terminated message in the Akka Stream GraphStage API. So we have the terminated message from the actor /$A because we don't have a little name in my target actor. And therefore, the logs say stream failed with a reason that we can inject inside. So notice that the Akka stream was also failed in case our business logic actor failed. So the notification goes back and forth if we have an error either in the target actor or in the stream itself. So this is a comprehensive example of how to be flexible with Akka Streams interacting with custom actors with the requirements that we outlined at the beginning of the video. I recommend that you consult the code in the GitHub repository. I'm going to link it in the description, as well as the written form in the blog post, which contains lots of explanations of how this mechanism works. I hope you enjoyed this video and found it valuable. If you did, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. And check me out on Twitter and LinkedIn. I post fresh updates on upcoming material. And check out my website at rockthejvm.com. I have hundreds of hours literally on everything in the Scala ecosystem, including Akka Streams and this GraphStage API. So until next time, folks, I'm Daniel, signing off.